So today I want us to focus on two main things. One is getting through this problem that involves curve sketching. So I mean, we just got through with chapter 3. We just got done with finding relative max, relative min, POI. But now let's look at it from a non-polynomial perspective. So this is now involving natural log, but also in the form of fraction. So there's more complexity, more involvement, but the concept remains the same. So it is a little bit like review, but from a different, using derivative rules that are different. Finding critical points is also algebraically look a little different as well. And then if we get done with this, then we will also look at some 5.1, 5.3 review. We can kind of begin our test review process. Yes?
Is this one specific for sheets?
Yeah, this is, well, under today's link, I put the key there. So you can just put this on a separate sheet if you like. Yeah. You can follow along with the key if you like. But I'm going to go through each step along the way. All right, so to begin, let's talk about natural log, because natural log has its own restriction in terms of domain. But then there's also another restriction from the fact that it's sitting in the denominator. So we have two things going on. I think it's helpful if we can figure out some domain restrictions, because those domain restrictions will kind of carry itself down through each of the derivative sign lines that we create. Okay, so one thing I noticed is natural log has its own restriction. And if you think about a natural log graph, the restriction is that natural log doesn't exist in the negative side of things, right? It's only existing to the right of 0. So we know natural log itself is going to just exist from 0 to infinity. But then there's another restriction in the fact that it's in the denominator. And what do you know about denominator in general? Yeah, we can't, I mean, whatever makes it 0, we know there's an issue there, right? We know that the graph doesn't exist. So let's figure out what causes the denominator to be 0. And that's going to be an additional restriction that we can add on to something that we already know, no negatives. And if we're trying to figure out when is natural log of x equal to 0, we can consult the graph or we can solve, right? We know that x is stuck inside the natural log expression. I want to undo natural log, so I want to involve the inverse function. So if I raise both sides base e, that gives me a clean way to solve for x. I get x equals e to the 0. And what do you know about anything raised to the 0 power? Is 1. So what's happening at 1 then? There must be a what? Good. Vertical asymptote. So we know there is a break at 1, and we know that our graph can't take in any negative numbers. So both of those will kind of help us create our full restriction in terms of our domain. So we know our graph is only going to be positive, so it starts at 0, but then there's a break at 1. So basically no negative numbers and no x equals 1. So we'll have to indicate the values that are around those restrictions. So there's our domain. Next step, we want to work towards finding relative extrema, which means we want to find the derivative. From the derivative, we can find critical points. From critical points, we can populate our sign line and then test intervals. Okay. So let's find f prime or y prime. We can't expand anything, right? This is kind of stuck in this form that we have. If we want to find the derivative, we have to involve what? Quotient rule. So I'm going to have you guys try this. I'm going to set up what we need for quotient rule. Okay, I'll go through every step along the way, but I want you guys to try it, and I also want to kind of give you a preview as to what's happening after this. After you find the derivative, what do we do next?
Set equal to 0.
Okay, which part's equal to 0?
Both the numerator.
Good, numerator and denominator. Okay, even though denominator may give you a vertical asymptote again, we still want to set it equal to 0 because it will help separate your intervals. Okay, good. So find the derivative first, then set numerator and denominator equal to 0. After you find those critical points, populate your sign line, choose values to test against your derivative. Okay, you don't have to do all that all at once, but in case you're working ahead, I want to kind of recap what steps to see. All right, so try that. I'm going to kind of walk around and see if you're stuck or if you have any questions or you need me to help you with the next step. Okay, guys, as a reminder, derivative for natural log, right, u prime over u. Once you find your critical points, place them onto your sign line. But I'll go over each step. That's weird. Okay, so walking around, the steps look pretty good. F prime. Okay. Once you get to G prime, we have to look at natural log of x. The derivative for natural log of x is just u prime over u, so 1 over x. All over denominator squared. Okay, any questions up to this point? Okay, a couple things I want to point out. First, we can clean this up. X and 1 over x will just go away nicely to just be -1. Another thing is that this natural log of x squared is not eligible for expansion. We can't bring that 2 down in front. This is not the same thing as natural log of x to the second power. Notice the parentheses is over the entire expression, so this is kind of stuck in the form that it's in. Okay, so let's clean up our derivative here. Minus 1. And we can't take any of the natural log x's out, right? Attach the minus, this is kind of stuck the way it is. Good, so here's our derivative. Any questions here? Okay, so this is where we're going to look for critical points. We're going to be populating our sign line. We're going to be testing our intervals with the derivative as well. Okay, so both the numerator and denominator get set equal to 0. Okay, this side first, I want to solve for x. I'll move the 1 over to the other side. Natural log of x equals to 1. And think about order pairs, or you can just go ahead and solve, right? Raise both sides, base e. That's a quick way for us to get rid of that natural log. This cleans up to be just x. X equals e to the first power, which is just e. Now look at where this critical point came from. This critical point came from the numerator, which means that this is a location where slope is equal to 0. Okay. We don't know yet if it's a relative max, relative min, but we do know it's a slope 0. Okay. The denominator, we're also going to look for critical points there. We can't bring the 2 down, but we can take the square root and get that 2 to just go away. I want to solve for x. Again, x is stuck inside natural log. I'm going to raise both sides, base e. I get x equals e to the 0 power, and anything to the 0 power is what? 1. But look at where this came from. This came from the denominator, so this tells us that this is a what?
Undefined.
Undefined. And also, it's a carryover from the beginning, right? We knew that 1, there's a vertical asymptote there, so as soon as you find a restriction, it's going to keep showing up in each iteration of your sign line. Good. So we have our critical points at 1 and e. So we're going to go to our sign line. Is there anything else I should put onto my sign line? There may be another critical point not showing up that'll be good to put onto our sign line.
0.
Okay, why 0?
Because that's where the graph starts.
Good, that's where the graph starts, right? We have no negative numbers, so if I ask for interval increase decrease, and you want to find the interval here, you're going to have to start at 0, right? So 0 is a starting point for our problem. It's nice to have some domain information to kind of help us. To help remind us, visualize that there's no negatives in our domain. Okay, so let's choose values in each interval. 1/2 falls nicely between 0 and 1. Between 1 and e, well, we know e is around 2.7, so 2 is a number that we can put. Now, a number to the right of e, you can choose 3. There's no issue there. You have your calculator, but without a calculator, I like to choose values that's easy to find. So I like to have values in terms of e. That's just my preference. So if I have e squared, I know it's greater than e, and it's also going to be a clean way of cleaning up and getting to a number without having to go through messy fractions or decimals. But really, you have your calculator, so you can choose any value you want. Okay, so I'm going to start plugging values into my derivative to see if it's a positive or negative value, and then from there I can interpret whether that interval is going to exhibit positive or negative slope. So 1/2 goes in for x. Natural log of 1/2, right? You can use your calculator, but just by some properties, I know natural log of 1/2 is going to land here. I know it's a negative, maybe negative 0.5. So negative 0.5 minus 1 is still negative. The denominator, the benefit there is denominator squared. So your denominator is always positive. So negative over a positive is going to be negative. I know my graph is going to be decreasing. Okay, next up, I want to plug 2 in. So if I plug 2 in for x, natural log of 2 is going to land somewhere here, which is somewhere between 0 and 1, so maybe 0.5. So imagine 0.5 minus 1, that's still negative. Denominator squared, so negative or positive is still negative. Okay, so now moving on to e squared. If I put e squared in for x, here's the nice thing about e squared. It allows us to get to a numeric value quickly. Natural log of e squared, if I bring that 2 down, I know that's just equal to 2. Natural log of e goes away. 2 minus 1 is 1. 1 over a positive is still positive. So there's my sign line filled out. What can we conclude based off of the sign line? There must be a what? C relative minimum. At e. Good. And if I want to find the physical location of that point, I have to go back to the what? Original. No. So e over natural log of e. You know natural log of e is already 1, so e over 1 is just e. So x value e, y value e. And the reasoning is because f prime changes from negative to okay. Any questions with f prime? Okay, so we have to find the second derivative because that's where we're going to find our points of inflection and concave up concavity behavior. So we have to start here, right? What's involved if I want to find the derivative from here?
Quotient and chain rule.
And chain rule. We can't bring that 2 down, right, without changing my overall value. So this is stuck the way it is. Again, we can't expand that denominator, and that's going to force us to have to consider outside, inside for our derivative, which is chain rule. Okay, so let me set that up and then see if you guys can try it. So when you get to the G prime portion is where you're going to have to involve chain rule. And then there's an outside we got to worry about. There's an inside we have to worry about. And we'll take turns with each of their derivatives, and all that's going to go in this space. Okay, and here's your f prime again. F and G. when you get to your second derivative, your numerator is going to look rather messy. We're going to find critical points, but to speed up the process, we're going to look for common factors in our two regions, in our two terms. And the idea is that if we can take a common factor out, or multiple common factors out between in my numerator space, then the rest of the expression can be combined a lot quicker, a lot faster, and it'll move to a place where we can find critical points more efficiently. But that's, I'll go over that with you in details on your preview if you're working through your second numerator. So this -1 is outside the natural log. It's not natural log, it only sees x minus 1. So it's just going to be 1 over x.
Oh, yeah.
Or,
Okay, yeah, then that.
and then your g function.
Yeah.
So what was your question?
I had a relation.
Okay, that's one. Just So, all the
Oh, well, I just like combined the two since they were both over X. Oh, then we have everything over X.
Now, that 2 is outside this region. Check the natural log minus 1. Yes. All right, so f prime. Yeah, I realized walking around, some students may consider the x minus 1 as inside the natural log function, but that -1 is completely outside. So that -1 is a standalone constant. So that derivative will just go to 0. So that's why the only thing that's left from here is just 1 over x. Okay. Times the original function of g. Back to f. And then g prime. So now this we got to do chain rule. So we got the outside portion, which is the parentheses squared. You got the inside portion, which is the natural log of x. And then we're going to take turns with each of their derivatives. So parentheses squared becomes what?
2 parentheses.
To the first power, good. And we don't do anything with the inside, right? We just copy that down. And then we look to the inside derivative, so natural log of x becomes 1 over x. All over my denominator squared. So denominator squared is going to turn into a what? To what power? To the fourth, right? If I have 2 exponents next to each other, they're going to end up being multiplied with each other. All right. Any questions up to that point? Okay, so if you're looking at that, that numerator looks messy to try to get to a point where we can find critical points, right? So what if we do this? What if we think of this as two separate terms, because all these are being multiplied together, and then there's a separation of minus, and all these are being multiplied together. Why don't we consider these as two separate terms and then look for common factors, right? If I can find a common factor or factors between these two parts, I can bring that out, and once that's brought out, then everything else will just condense a little faster. So what do you see is shared between this term and this term? Okay, ln x, what else? 1 over x. So we can take 1 over x and ln of x, pull it out in front, and remove it from both terms, and then the leftover can just be in its own separate parentheses. So we're going to take a 1 over x and a natural log of x out of both terms, and then the leftover will go in its own space. So if I remove 1 over x and natural log of x out of this expression, what's left over? Just ln x, right? Because I have 2 to begin with. I remove 1, I remove this, I still have a natural log of x left over. Okay, good. Okay, now moving on. If I remove 1 over x and natural log of x, what's left over?
Would it still be ln x minus 1 is attached to the negative 1?
It's attached to negative 1. Okay, this, I was talking about this factor and this factor, right? If we remove both of these, we're left with the 2 and the natural log of x minus 1, right? Okay. I'll put the 2 in front, just makes it easier for me to distribute later. Okay, any questions there? Do you guys see how we took out the common factor? And also you see how this is going to become a lot easier to manage, right? Things will combine a little faster once we get this cleaned up a little bit more. Everybody good so far? Yeah.
Could you not have pulled out ln x squared?
Right, we can't pull natural log of x squared. Are you thinking that maybe this 2 can be brought up?
No, because there's 2 terms of ln x on the right equation. And there's also 2.
So there's two natural log of x's here, but there's only 1 here.
Is that minus 1?
Yes, that minus 1 is connected. Yeah, so this natural log of x minus 1 is not eligible to be a factor that's part of natural. Yeah, so these are completely separate things. Yeah. Yeah, then if that minus 1 wasn't there, then yes, then we can take out natural log of x squared. Yeah, but that minus 1 kind of complicates things. Okay, good. Anything else? You guys good with the
Would you not have canceled out the ln x squared over the ln x to the 4th? And
Right.
have just an ln x squared in the denominator?
Right. Why can we not take this natural log of x with this? What's preventing us from being able to take out the natural log of x here? Yeah, that minus is adding to that complexity. Now, once this is out, you see this natural log of x? This is free to match with the denominator, but not at this stage because of that minus sign. Okay. Good. Anything else? There's a lot of moving parts, right? So I want to answer any question you guys have. Now moving into my bracket here, this is a little cleaner than what I had, but I still need to do a little bit of work to get this to a point where I can combine some like terms. So what if we do this? What if I distribute the negative through and I have natural log of x minus 2 natural log of x plus 2. Now I have we have like terms there. This will become negative natural log of x. We can take out one of the natural log of x's now because there's no more attachment with addition or subtraction. And then one other thing is that this x is in the denominator, but this natural log of x is also in the denominator. I know they seem like they're in different spots, but they're both denominators, and we can kind of just merge those two denominators and just have them share the same space. So here's my cleaned up f double prime function. I got the x and natural log of x to be in the denominator space, cubed. And then this becomes 1 natural log of x minus 2 natural log of x, which is negative 1 natural log of x plus 2. Okay, so here is my cleaned up second derivative. Okay, it's a lot more manageable here, right? Because we're going to have a much easier time finding critical points once it's in this form. Okay, questions? Okay, where do we look for critical points?
Or denominator.
Yeah, both locations. Okay, so all right, I'm going to tackle the numerator portion first. I want to solve for x, but x is stuck inside the natural log. Well, if I involve the inverse, I can rid myself of natural log, and that will isolate my x, and that will lead me to what I want. I want to solve for x. So I have e squared, that's a critical value that we can put onto our sign line. Here, I have two separate terms, so I'm going to set both equal to 0. This is already done. Here I can take the cube root. Remember, this is not expandable. I can't bring that 3 down, but I can take the cube root of both sides. And this keeps coming up, right? Natural log of x equals 0. And it's that vertical asymptote that's going to keep showing up. Okay, so we have 3 critical points. That's going to go onto my second derivative sign line. I want the 0 there, I want the 1, and I want the e squared. I'm going to choose values in each interval to test against my second derivative, so I'll choose 1/2. I can choose 2, that's fine. You can use your calculator, but I'm just going to use e. I know e is a value that safely falls between 1 and e squared. And then to the right of e squared, I'm going to choose something in the form of e. It'll just make things quicker for me to evaluate. Okay, so one piece at a time. I'm going to put into the second derivative and see whether it gives me a positive or negative value. Natural log of 1/2, we know that's a negative value. Negative times negative is positive. Positive plus 2 is still positive. Denominator, natural log of 1/2, that's negative. Negative cubed is negative. So I have positive over negative, remain negative. But we interpret negative for second derivative not as in terms of slope, but in terms of concavity, right? So concave down. Next up, I'll test e. Natural log of e is 1. Negative 1 plus 2 is positive. E natural log of e, that's all positive. So positive over positive is positive. Next up, I'll test e cubed. Okay, so let me show you what that looks like. Negative natural log of e cubed plus 2 over e cubed natural log of e cubed. Okay, I know my denominator is all positive, but my numerator, you see that 3 can come down nicely in front now that it's part of a natural log. Negative 3 plus 2 is negative, so negative over positive is negative, so. Okay, we have our second derivative sign line populated. Can we make any conclusion about points of inflection?
So points of inflection at 1 e squared.
Because you're looking at change in signs, right? Now, do we have to be careful about one of these values?
1 because it's vertical.
Okay, yeah, so it's a vertical asymptote. Even though there's a changing in cavity, that point doesn't exist, so this is out of the running for point inflection, not a point inflection. E squared is safe, right? E squared does sit on the graph. We know there's a point of inflection there, so the only point of inflection is at e squared. So it's nice to have that domain foundation, right? If we have this anchor kind of information about the graph, we can always think about, wait, is there something that's a little bit off? Because if we're just relying on the signs, we may make an incorrect judgment call. But because we know information about our critical point, we know that the graph doesn't exist there. We can conclude that, okay, even though there's a change in sign, I know I know there's no point of inflection there. And then to find the y value, goes back to the original function, right? It's going to end up being e squared over 2. Back into the original function. Let's go to the 5153 properties worksheet. It's also under today's link, but we're going to skip most of the first parts because they're all just expanding, condensing. We're going to go directly to the derivative because, well, we have some expansion to do there as well. So are we good here? Okay. So on that handout, that worksheet, can you guys look at number 6? We're going to find the derivative of that expression. Is there anything that we should do before we jump into our u prime over u? Let's expand, right? We don't want this entire thing to be our u value, right? That's a messy derivative to have to go through. So why don't we expand? Take care of the radical, take care of the rational exponent, bring that down. And once you have everything cleaned up, you should have easier derivative rules to find, or easier derivative problems to solve. Okay, so try that. If you get done with 6, try number 9. And that's the b plus 7. This one is going to be outside. The 656 is going to come down all the way to functions. It's going to be here. So if I can just get the one out here, we're just going to come down to that. First, the square root becomes 1/2 of that one. That's the expanded form. 45. So here's the thing, is that this x can't distribute through because order of operation prevents it. Just that 1/2 takes precedence, so you gotta make that same thing. Then you have Okay, your steps look pretty good. Let me share the work here. All right, so expand first, right? If you're in the middle of a messy derivative rule, that means, and it's a natural log problem, that means we didn't go far enough with our expansion. So let's think in terms of natural log of a plus natural log of b, right? My a value is my x, my b value is my square root. I separate them out, natural log of x plus natural log of square root of 6 minus x cubed. Bring that 1/2 down in front. And now we have a much easier derivative problem to solve. Right? It's going to be u prime over u prime over u. No need to find common denominators. If you leave your answer unsimplified, that's fine. Questions? Okay, let's look at number 9. This is on the back page. So, do you see any logs in this problem? No logs. Okay. So this is a candidate for log differentiation. Log differentiation is where we introduce logs into a problem that has absolutely no logs in it. The reason why we do that is because we want our equation to be, we want to take advantage of log properties, right? So the idea is if I introduce logs into the problem, then I'm going to have all these log properties now available to me to use. And the reason why we would do that is because we could maybe avoid messy quotient chain product rule if we force this into a log problem. So we'll take the natural log of both sides and see which properties show up. So here's a hint. If natural log of AB over C, how would you expand something if it's natural log of AB over C?
So it would be A plus B minus C?
Yeah, but then they're all going to be natural log, right? So natural log of A plus natural log of B minus natural log of C. So that's the same approach that we're going to take with this one. I have 2 terms up top. I have 1 term below. My numerator terms is going to be part of a positive natural log, and my denominator term is going to be part of a negative natural log. And then once we have them separated, we can deal with the radical and the exponents, and we can start bringing them down as well. exponents can now come down, right? We still want to expand. We don't want to do derivative, not yet, not quite yet. Every term is expanded as much as we can do. And now all that remains is derivative, right? And u prime over u is going to apply for everything we see, even the left side. But that natural log of y, we got to do some additional step implicit. So do you guys remember what's going to happen with that natural log of y? What's the derivative there? Yeah, after 1 over y, right? We got to do 1 over y and then dy dx. Okay, and now the right side, you can do u prime over u for every term. The coefficient is just going to tag along to the derivative of the variables. Okay, how do I get dy dx by itself? Okay, which is the same thing as multiplying by y, right? Okay. So just understand that when you do log differentiation, your answer is going to be messy, but it's okay. As long as you have all the parts there, you're good. Don't worry about how do I clean this up. Just get dy dx by itself, and whatever's left on the right side, that's good enough. But there's one more thing that we're going to do after this, though. Okay, so we have dy dx by itself, which is good, but the right side, we have one final substitution that we can make. What can I replace this with?
Oh, well, the original.
Yeah, so we started with a function, so we should be able to represent our derivatives with no y's in it. Our derivatives should be just, we can represent everything in terms of x. There's no need for y to sit in our derivative. Okay, which will mean that your derivative will just look a lot messier. Okay, any questions? Okay, so a couple of things I didn't get to today, implicit differentiation and also inverse of derivative at a point. So maybe we can start Monday going over these two first. But essentially, we kind of begun our review already. I'll have a test review worksheet available for you guys to access before Monday. And we'll have Monday, Tuesday, Wednesday to review. Let me talk about recovery. So chapter 3, recovery. I'm going to be creating a Teams assignment with details about what to do in order to be eligible for that recovery. So here's the schedule. The schedule is going to be next Wednesday, the recovery assignment is due. Next Thursday is your test, and next Friday is your recovery test. And then they keep changing the policy, but the new policy now is if you make under an 89, you're eligible to recover up to an 89. there's no more 79 issue. So anything below an 89, you can recover up to an 89. But the requirement for us is we need to have our prerequisite assignments done before we're eligible to do that. Another thing is some of you did do your recovery assignment for the quiz to gain that point back. So that may take a little bit longer. I'm gonna try to work over the weekend to see who did the assignment, and if they did better on the test, if they did better on test, I will replace that with the quiz grade. Or I'll replace the test grade into the quiz grade. Okay. Okay. Any questions there? All right. If you're on Teams, have a great weekend. I'll see you guys Monday.
Have a nice weekend.
You too. Have a good weekend.
Thank you, Mr. Yang.
Thank you.
Thank you, Mr. Yang.
See you guys.
Thank you, Mr. Yang. I don't know if you saw the remind, but that just lets you know why I wasn't in class today.
Got it. Okay. Thank you. See you, Mason.
Bye.
Bye.